let us talk about the first law of thermodynamics. Now, the first law of thermodynamics is actually quite simple. It simply says that the internal energy of a system is equal to the sum of the heat supplied to that system and the work done on the system. This is actually simply conservation of energy. And a simple way to think about it, well, there are just two ways in which you can change the internal energy of a system. Number one, give it heat, make it lose heat. Number two, do work on it or make it do work. So let us understand how we adjust each of these things. So we want to make sure that we understand the positive conventions of these things. So of course, for internal energy is considered positive if it increases. Heat or Q is considered positive if it is supplied to the system, and work is considered positive if work is done on the system. Right? And of course, we put in the corresponding negative conventions. Okay, delta U is negative if the internal energy decreases. Q is negative if heat is lost by the system, and W is negative if work is done by the system. So how well, okay, so Q is quite straightforward, right? If you put a flame under it, positive, right? If the system is very hot and the surroundings are very cold, Q is negative. But the tricky one is W. When is W positive and when is it negative? Well, the simple rule of thumb is, right, we always do work on the system if the system is compressed or if there's a loss in volume, right? Think about it. If you want to compress a system, it requires a force from outside to push it in, right? And work is done by the system usually if there is an expansion, okay? And so the volume increases. Okay, so if something increases in volume, it's because it's pushing from within. So the system has to be the one doing the work, right? So a nice way to remember this, of course, also remember that the work done by a system, particularly a gaseous system, okay, this is usually used for gaseous systems, in fact, ideal gases. Work done is defined as integrate P dV, okay, which is simply the area under a pressure volume graph. Okay, a lot of times you'll be given PV graphs, and so the area under any given change of the PV state gives you the work done on or by the gas. Delta U, there's also a nice way to think of delta U. Remember, if your system is an ideal gas, and typically it will be, then delta U simply equals to the change in the kinetic energy of the system, which we have seen before equals to 3 over 2 nk delta T. So that's a nice way to think of it, which shows that delta U for an ideal gas is also directly proportional to the change in temperature. And this is a very important relationship to remember. Okay. Now, just for us to be aware of this, 3 over 2 nk delta T can also be thought of as 3 over 2 nr delta T in case we are thinking in terms of the number of moles, or because of the ideal gas law, PV equals to nkt, then this can also be 3 over 2 delta, the product of the change in the PV state. Okay, so here we are. That's your first law of thermodynamics and all the associated sub-formulas that you may use with it.